Hello and good afternoon friends, welcome to the CEC-UGC live lecture. Dear friends, with another lecture on chemical thermodynamics. Today we are going to talk on first law of thermodynamics, and for this we have again with us in our studios Dr. Amit Kumar. Dr. Kumar is Senior Assistant Professor in Department of Chemistry, Dayal Singh College, University of Delhi. So dear friends, let's take advantages from his experiences and try to understand the first law of thermodynamics. So first of all, I would like to welcome our guest, Dr. Amit Kumar. Dr. Kumar, welcome to the EDICET lecture.
Thank you
As
very much.
we know that we are carrying a series on chemical thermodynamics, and it is the third lecture in this particular series, and today we are specifically going to talk on first law of thermodynamics. So I'm handling this lecture to you, sir.
Thank you very much, Kitika. First of all, I wish very good afternoon to all my listeners. Dear friends, we have been having 2 lectures on these topics, 2-3 lectures on the subject matter of thermodynamics, where we have been handling some basic concepts, and thereafter expansion work we have also covered. After the discussion of expansion work, heat, and now it is time, as we said in the last lecture, that we would be devoting our attention towards the discussion of first law of thermodynamics, because after the discussion of heat and work, these are 2 equivalent ways of changing the internal energy of the system, and the first law of thermodynamics basically forms the basis of concept of internal energy. Besides the formulation of the basis of concept of internal energy, it also denies the existence of perpetual motion machines of the first kind. And then this first law of thermodynamics is also known as the law of conservation of energy. So in this talk, with starting from the very discussion of how first law of thermodynamics came into existence, because as I said in the very beginning in my first lecture, that all the laws of thermodynamics are based on rich summaries of experience. So these are the laws which are summaries of experience, and now we would like to see how the first law of thermodynamics is the summary of the experience. Experience over a very wide variety of systems over a very long period of time. So with these objectives, we start the first law of thermodynamics. Before we carry on with the discussion of first law of thermodynamics, it is important to recall one important point, that is, what are cyclic processes. Cyclic processes basically are the ones in which a system from its initial state traverses some sequence of steps and finally returns back to its initial state. While doing so, there are changes which occur in the functions of the system, that is, the heat involved or the work involved. The heat involved, the small change in heat involved, that is dq, or the work involved, dq, in very small step, if we take a sum of all these, this becomes equal to the total work or heat involved in the cyclic process. The work and heat are path functions, as we have already seen. So therefore these need not be a non-zero. These quantities would be actually a non-zero quantity, that is, there will be some heat, some work involved during the transformation of the process, and not necessarily be zero or not necessarily be exactly non-zero, but usually these quantities are non-zero quantities. However, on the other hand, if we look at the changes in state functions associated with the system, for example, if we look at the change in temperature of the system or the pressure of the system, there would not be any change in temperature or pressure of the system. As a result, we can say that dt would be 0, that is, its differential would be 0, that there would be no small change associated with the cyclic process. Now, let us have with this elaboration, let us have a look at how the first law of thermodynamics is formulated. First law of thermodynamics is basically a summary of the experience, which is as follows, that is, if a system is subjected to any cyclic transformation, the work produced in the surroundings is equal to the heat withdrawn from the surroundings. This observation is being made over a varied kind of systems over a large number of times. So, therefore, this is the experience, that is, if a system is subjected to any cyclic transformation, the work produced in the surrounding is always equal to the heat withdrawn from the surrounding. Now, it is important to note over here that here the cyclic integral dW, we have not placed a negative sign. This sign convention is in accordance with the sign convention in physics. We will also talk about how to write formula in IUPAC sign convention. In IUPAC sign convention, we just put a negative sign preceding the cyclic integral dW. So, therefore, this is the experience that cyclic integral of work is exactly equal to the cyclic integral of heat effect. That is, the heat and work effects are, the magnitude of heat and work effects are equal in a cyclic process. Now, having said this, moreover, in a cyclic process, the integral of any state function is 0. What it does mean, can we say it in other words, that if there occurs some state property y, then its cyclic integral, then the integral of its differential over a cyclic path would be 0. If it is true, then we can look for rearrangement of our equation number 1, which is just nothing but saying that cyclic integral of work effect equals to cyclic integral of heat effect. Now, we take the cyclic integral of work effect from the left hand side to the right hand side and rearrange the equation. We get this equation as cyclic integral in bracket dq bar minus dw bar equals to 0. Now, it is important to note that I am not spelling it dq, but I am saying it is dq bar and dw bar. That has already been emphasized earlier in my earlier talk. Here also I would press upon why we would write the bar over here. Now, having said this, now just recognize this equation number 2. Try to see that there is cyclic integral which is operating on a bracket term, and now cyclic integral of this bracket term equals to 0. Now, question arises, can we recognize this total difference of heat and work effect as small change in some state property of system, because we have already said as a converse that if there is cyclic integral of some property of the system, if its cyclic integral equals to 0, then we can recognize this property as some state property of the system. Taking this analogy, we can say using equation 2 that now we can define a state function, that is internal energy designated by symbol U, the differential of whose du equals to dq, the heat effect, minus the dw, the work effect. So, therefore, now in equation 4, as you can see, we have written that cyclic integral of du equals to 0. What does it mean? It means that internal energy is a state property of the system. So, now with this, if we integrate for evaluating the internal energy change for any particular change in state of a system, not necessarily for an isolated system, we can integrate equation 3 and we would write like as is in equation 5, that is integral from initial to final state, integral of du, the differential of internal energy, equals to the integral of heat effect and the work effect, and we integrate it to equation 5, where we get delta u as the result of integration of differential of internal energy from initial state to final state, which is equal to q minus w. It is important to note here that in equation 5 we cannot write delta q minus delta w. The reason being that heat and work effects are path functions, and therefore they cannot be evaluated as the difference between the heat which is associated with initial and final state of the system, or in other words also the work involved with initial and final state of the system. We have already covered in lecture 1, if you remember, that heat is only a quantity which appears only during the change in state of the system. Similarly, work is also produced or is destroyed, therefore appears across the boundary of the system only during a change in state. And since these are path functions and they appear only during the transformation of the system, we cannot write delta Q, as there is no heat associated with the initial state or the final state. Similarly, there is no work associated with the initial state or the final state. So, as a result, we cannot write delta U equal to delta Q minus delta W. We need to write delta U equal to Q minus W, that is the total heat involved in the transformation of the system and also the total work involved in transformation of the system. So, all these equations ranging from equation 1 to equation 5 which we have seen, these are equivalent form or mathematical form of expressing the first law of thermodynamics, which, as the rich summary of experience says, the cyclic integral of heat is exactly equals to the cyclic integral of work effect produced during the cyclic transformation of a system, because in the system when it undergoes a cyclic transformation, no net effect the system suffers in terms of change in state functions of the system. If this is so, then now we can, with the establishment, this is how the first law of thermodynamics establishes the concept of internal energy as a difference between the heat effect and the work effect produced during the transformation of the system. With this, conceptualizing the internal energy of the system and the statement of the first law of thermodynamics, usually if you see in books, the statement of first law of thermodynamics is also written as the law of conservation of energy, that is, energy can neither be created nor it can be destroyed, it can only be transformed from one form to the other. By an illustration, we can understand this point, how the first law of thermodynamics guides us to the law of conservation of energy. You see, let us suppose we consider a system, suppose for example a piston cylinder arrangement if we have, that is lying in a particular room. So, this piston cylinder arrangement becomes our system of interest, and the whole volume of the room having its inner wall, this becomes its immediate surrounding, and now we can design the wall of the room in a way that there is no heat or work effect this particular composite system. What we mean by composite system? The system of interest, the piston system arrangement, piston cylinder arrangement and the room taken together, the whole volume of room taken together. Both these entities make a composite isolated system, because we have designed the walls of the room in a way that there is no communication by virtue of heat effect or work effect of the inside of room from that of outside of room. So, we can say that this room now makes a composite isolated system having a system of interest which is having piston cylinder arrangement, and there are other entities present inside the room. The whole volume of the room becomes the immediate surrounding to this system of interest. Let us represent the system of interest with symbol A and the immediate surrounding with symbol B as shown in the projection. So, therefore, now we can say that with this consideration, let us say that there is some change in internal energy of this composite system occurs, that is this composite system, that is system AB, that is the total room, that undergoes because that is not involved in any kind of heat or work effect with the total complete surrounding. So, therefore, there will be no change in internal energy of this composite isolated system. that will be, that is delta UAB equals to 0. Now, this total change in this isolated composite isolated system, total change in internal energy, that is delta UAB equals to change in internal energy of system of interest, that is delta UA, that is of system A, plus the change in internal energy of its immediate surrounding, that is the whole volume of the room itself. So, therefore, now this sum equals to 0. What it does mean is that the change in internal energy of the system of interest, that is system A, is exactly equal to the change in magnitude of internal energy of system B, that is its immediate surrounding, but with a negative sign. So, what does it mean? So, in an isolated system, in one region, suppose there occurs an increase in internal energy, then obviously the same amount of decrease in internal energy would be observed in another region. Hence, it does mean with which this we can say that in an isolated system, the total energy of an isolated system is constant, using which only the Clausius has given a famous first law statement of thermodynamics, according to which the energy of the universe is constant. Now, coming over to the point how the energy of the universe is constant, we can consider the whole universe to be made up of a large number of such composite systems which are isolated from the rest of the world, rest of the portions of the universe, and therefore, they cannot communicate in terms of energy effects, in terms of any energetic effects with the rest of the universe, and therefore, considering the such myriads of large number of such composite systems within the universe, we can say the energy of the universe is constant. This is how Clausius came to this conclusion, and stating it's the first law of thermodynamics in a way that energy of the universe is constant. This statement also becomes the form of statement of the law of conservation of energy. What the law of conservation of energy says? It says that energy can neither be created nor it can be destroyed, it can only be transformed from one form to the other. As we have seen in the Clausius statement of first law of thermodynamics, he says energy of the universe is constant. It does mean we cannot create energy, neither we can destroy it, we can only convert it, we can only transform it from one form to the other. Now, coming over to the third point, how the first law of thermodynamics denies the existence of perpetual motion machine of first kind. For this, we need to understand what is a perpetual motion machine of first kind. A perpetual motion machine of first kind is the one which would absorb no energy, and without the absorption of energy, it will produce work effects. It sounds at this moment, it sounds very odd that without any absorption of energy, some machine would be there which would produce work. But at the time when the concepts of thermodynamics were under developing, at that point of time, there were people who used to befool others, and we used to create serious frauds by saying that I have designed some machine which would work without the absorption of energy. So, to account for that, it is being documented now as a concept called perpetual motion machine, and it is the first law of thermodynamics which denies the existence of any such machine, because first law of thermodynamics says we cannot create energy. So, therefore, there cannot be any machine which can, without the absorption of energy, can produce work for us. So, first law of thermodynamics is also the denial of perpetual motion machine of the first kind. Having said this, let us now have a look at the difference between the first law of thermodynamics through this projection. In this projection, now you can see we have compared the equations of first law of thermodynamics in physics and in IUPAC system, that is chemistry. The students always encounter a difference between the sign conventions of work in IUPAC system and in physics, and this leads to a utmost confusion in their mind as to what happens Why this sign convention is different? You see, as we had made it very clear in the first lecture itself, that the work produced, the emphasis of the physicists is on producing work in the surrounding, and whenever the system raises some mass object, then it is said that it has lifted some mass, and it means the work is being produced, and in that situation the work is given a positive sign. However, in IUPAC system, anything which lowers its internal energy is given a negative sign, and whenever work is produced, that is, the work is done by the system, it is at the expenditure of its internal energy, and that is the reason why it is given a negative sign. Now, if you remember when I started in today's lecture, I did give a rich experience of the first law of thermodynamics based on the experience. The experience was that cyclic integral of heat effect is exactly equal to the cyclic integral of work effect. Moreover, I did emphasized over there, here only the positive sign is been included, and this is the equation which is applicable only in the physics. But when the same equation is considered in chemistry, then it becomes cyclic integral dq equal to negative of cyclic integral dw. So, you can see in physics we have this form of first law, that is delta U equal to Q minus W, you would have seen in earlier projections, and now with that difference in sign convention, the first law equation is changed in IUPAC system. Here we have delta U, the change in internal energy of the system, as the sum of heat and work effects, that is the work done on the system. So, therefore, now if we rearrange these equations, they take the form Q equals to delta U plus W in physics, whereas Q becomes equal to delta U minus W in IUPAC system. Now, by definition, work is a positive quantity in physics. So, therefore, work equals cyclic integral, work equals integral from initial volume to final volume P dot dV. Similarly, the work by definition over here in IUPAC system is just nothing but the same equation with a negative sign. So, over here you can easily see that however the magnitude of work involved in both the IUPAC system and in physics is being the same, however sign is just the different, and if we substitute the value of work involved in the respective equations of the first law, what we get is Q equal to delta U plus integral V1 to V2 P dV as the heat involved, and similarly here also in IUPAC system we get Q equal to delta U plus integral V1 to V2 P dV by substitution of the work involved from this equation. So, therefore, we can see easily, although the work effects is given, work effect being produced in the surrounding is given different sign convention in IUPAC and in physics. However, the ultimate equation of the first law of thermodynamics using the elaborative expression of work involved becomes the same. Now, you can see same heat effect, same internal energy effect we would observe. So, it is merely a basis of calculation in different sign conventions, and students should not feel any fear about them. Coming over to the internal energy as a concept which the first law of thermodynamics forms. We see that total energy of the system, we have seen that whenever heat given to the system, we have already said that it raises internal energy of the system. Whenever work is done, it also raises internal energies of the system. Now, if you look back in the first law equation, the first law equation only determine the changes in internal energy of the system during its transformation from one initial state to final state. It is a very important point to understand that first law of thermodynamics does not defines the internal energy. It only makes the basis of concept of internal energy and actually determines the change in internal energy of the system when a system undergoes a transformation from initial state to final state. Now question arises, is there any method exists by virtue of which we can determine the absolute internal energy of the system? So the answer to this question is simply no. We cannot determine exact amount of internal energy associated with the system. Why we cannot determine the exact amount of internal energy associated with the system? The reason lies, we can have a look at the projection itself and we can understand by definition of internal energy. It says it is suppose now we define the total energy of the system. What is total energy of the system? Let us consider this point first to understand what is internal energy. Total energy of the system, suppose, is represented by a symbol E, is a sum of kinetic energy of the system as a whole. What I mean to say by saying kinetic energy of the system as a whole means that suppose your piston cylinder arrangement is your system and it undergoes a motion from one point to the other, then it is having kinetic energy by virtue of motion of the system as a whole. Similarly, if the potential, it also has total energy of the system also has, apart from the kinetic energy, the potential energy of the system, that is potential of the energy of the system as a whole. This is due to the presence of external fields. For example, there is gravitational field, there are very many other kind of fields which are present, which raises the potential energy. That is, suppose if the piston system arrangement is your system, piston cylinder arrangement is your system, and if it gets elevated and lowered during the transformation of the system, then it does mean it also possesses the potential energy as a whole. Plus there is a third term called internal energy. What happens actually, we consider for all practical purpose our system is at rest, that is our system as a whole does not move. Our system is not considered as being influenced by presence of any kind of force field. By virtue of these considerations, the kinetic energy of the system as a whole becomes 0, the potential energy of the system as a whole becomes 0. Now the total energy of the system becomes exactly equal to only its internal energy. Only its internal energy. Now it is therefore important to know what is internal energy. The internal energy is basically the sum of all types of kinetic and potential energies due to interactions between all types of particles constituting the system. What we mean by saying this? Suppose now if we have a piston cylinder arrangement, we consider this as our system, and in the system if we suppose we have a gas as the working substance. Now the gases particles would continuously be set in motion, maybe the gases atoms or molecules, and by virtue of their motion they possess this kinetic energy. So this kinetic energy, as a result of motion of the particles within the system, they contributes toward kinetic energy. There is various kinds of potential energy, that is the potential energy due to interaction between the atoms and molecules together, and within the atom and molecule the interaction between nuclei, electrons, different kinds of potential energies. So we can say the internal energy of the system is just nothing but is the sum of all kinds of kinetic and potential energies of the constituting particles within the system. This is how we define the internal energy of the system. And now since we cannot determine at the microscopic level what is the force between the different particles, even considering the statistical interpretation, statistical thermodynamics, it is very difficult to determine these interactions and to actually estimate these potential energy terms, and therefore we cannot, as a result, we can define internal energy as a sum of all kinds of kinetic and potential energies due to motion and interaction of particles within the system. We cannot actually determine the exact values of value of internal energy associated with a particular system at in a particular state. What we can do is, whenever a system undergoes a change in state, it undergoes a change in state by virtue of change in state variables, and the change in these state variables which we can determine, and correlating it with the internal energy change through the first law of thermodynamics, we can determine the change in internal energy of the system as the heat effect and the work effect with which the system is involved. Now, let us see that, just have a look at the projection. Now, we are considering certain equations where we have the first law of thermodynamics, as we can see that it says that change in internal energy equal to Q minus W according to the sign convention is in physics. Now, you see this Q and W is just nothing but the heat and work effects. Now, the heat and work effects are path functions, that is, if suppose a system undergoes a change in state, then during the change in state we need to evaluate how much heat is involved during the transformation of the system and how much the work is involved. Then only we can determine the change in internal energy of the system during the transformation of the system, if we want to determine it purely from the first law of thermodynamics. Since it is a very cumbersome process to continuously keeping track of the system during the transformation of the system. However, on the other hand, evaluating the values of state functions, state variables such as temperature, pressure and volume, they are readily measurable, they are easily measurable quantities. Before the change in state is affected, we can determine their values in the initial state, and after the change in state is affected, we can determine the value of temperature, pressure and volume in the final state. So, therefore, correlating with the change in these values, we can determine the internal energy. Now, it is important to understand how we can do that. For this, let us suppose that U, which is a symbol designating the internal energy, U suppose is a function of, since U we have just said that U is the internal energy is a state function. So, this internal energy will be a function of other state variables, the temperature, the pressure, the volume. And now, if we consider that our system is in the constant composition state, that is, during the transformation of the system, the composition of the system does not change. And if you recall back in the first lecture itself, I said the thermodynamic variables of interest, state variable of interest in thermodynamics are temperature, pressure, volume and the composition term. Since here we are saying that suppose composition of the system is constant, then we have only temperature, pressure and volume as those variables which can undergo a change in state, which can undergo a change during the change in state. Now, there are three variables. You see, the fact of matter is that if there are these three variables, there would also be certain equation of state relating these three variables. That is, the change in temperature and pressure if are known, then it can be correlated to change in volume. Such an equation would be called as an equation of state. It does mean if we know the values of two, the third one becomes automatically known by virtue of knowing the relationship between temperature, pressure and volume. And this relationship comes from equation of state. Now, having said this, it does mean only two of these three variables, that is the temperature, pressure and volume, are naturally independent, and we can therefore consider internal energy as a function of any two of these temperature, pressure and volume variables. Now, for practical purposes, let us consider that internal energy is a function of temperature and volume. Having said this, we can write the complete change in internal energy, that is the differential du, as the contribution of two terms. First term is the contribution which makes its contribution towards the change in internal energy due to change in temperature. The second term gives the contribution towards the change in internal energy due to change in volume alone, keeping the temperature constant. In the first term, volume was kept constant. What it does mean? It does mean first term gives the contribution, suppose when the system undergoes only a change in temperature of the system and volume of the system is kept constant, then in that situation how much internal energy it will produce, the first term amounts this thing, and the second term in equation 10 amounts the change in internal energy due to the change in volume itself while keeping the temperature constant. And now let us understand these terms again. Now if you look at this, the first term is basically a partial differential which expresses the del u, which we can read it as, if we write the equation just mathematically, we would be able to read it as the rate of change of internal energy with temperature. It gives you an idea of how the internal energy changes with change in temperature, that is rate of change of internal energy with temperature keeping the volume constant. Now if we know the rate of change of internal energy with temperature and then when we multiply this quantity with total change in temperature, what we would get? Total change in internal energy due to change in temperature alone keeping the volume constant. Similar interpretation can also be looked at for the second term. Here in the second term we have again a partial differential that we can read it as del u by del v. What does it mean? The del u, the change in internal energy with respect to the change in volume, or in other words we can also say that it is the rate of change of internal energy with volume keeping the temperature of the system constant. Now if this rate is of change of internal energy with respect to volume is known, and if we multiply this quantity with the total change in volume, what we would be able to get? We would be able to get the change in internal energy with respect to change in volume at constant pressure. So therefore, at constant temperature, that is the temperature of the system is kept constant. So by considering the two terms, we will have total change in very small change in internal energy of the system. Now we had from the first law of thermodynamics, if you recall back, by substituting the value of work effect, the internal energy change, small change in internal energy can be correlated to dq, the heat effect, minus P of dV, that is opposing pressure times dV, the work effect. Now this becomes equal to taking this equation 10 also into consideration, here also this is equal to du, and this left hand side of equation 1 is also equal to du. So by taking this we make equation 11, which says that dq minus p opposite dv equals to delta u by delta t at constant v dt plus delta u by delta v at constant t dv. Now a point comes that if we want to calculate the finite change in internal energy, then all we can do is we can integrate equation 10. But to do so, what we need to do? We need to evaluate these partial differentials, that is the rate of change of internal energy with temperature and the rate of change of internal energy with volume. If we are being able to evaluate these partial differentials, then only we will be able to correlate them with certain known experimental quantities with small change in internal energy, and we can integrate the equation 10 in that situation, and then only we will be able to determine finite change in internal energy of a system for a transformation of system from initial state to final state. In order to determine these partial differentials, let us see how we proceed. Once again consider this equation 11. In this equation 11, now suppose we keep the volume of the system constant. If we do so, consider this equation 11, here dV, the change in volume, would be 0 then, because we have kept the volume constant. Similarly, considering the left hand side of equation 11, here also we have in the second term dV, that is the change in volume, and since volume of the system is kept constant, so this second term of left hand side would also be set equal to 0. Now having said this, then this equation 11 under the condition of constant volume transforms to dq equal to delta u by delta t at constant v dt, that is we have equation 12. Now, if you make a note of the point that in equation 11 there was only dq, but we have put a subscript, v over here also. What it signifies is that this change in heat, that is this heat effect dq, small heat effect, is basically occurs under the condition of constant volume, and this dqv equal to rate of change of internal energy with temperature at constant volume, and when we multiplied with the change in temperature. Having said this, now have a look at this, that how we can do some mathematical manipulation to correlate this partial differential with the experimentally determinable quantity. Now, suppose if we divide this whole equation 12 with dt at keeping the volume of the system constant, then what you will have? You will have dqv by dt equal to delta u by delta t at constant v dt. That is, we have divided equation 12 by dt. So, what we will have? dqv by dt equal to delta u by delta t at constant v dt. Now, let us identify this differential dqv by dt. This is just nothing but the heat involved, that is the heat involved or the change in heat, that is how much is the heat involved for a particular change in temperature of the system. If we define it a little bit more properly, then it is the heat involved in bringing a, if suppose we get the denominator as unity, so it is the heat involved in bringing a unit change in temperature of the system. And now this heat, if we know, then we can correlate it with the heat capacity of the system. So, we can define a new concept called heat capacity. Now, here it also it also has subscript v indicating that heat capacity has been defined under condition of constant volume. That is, heat capacity at constant volume is just nothing but the heat involved in bringing a unit increase in temperature of the system, because whenever heat enters the system, this dqv would be a positive quantity, and whenever we know that whenever heat enters the system, it raises internal energy, and therefore which gets reflected in temperature increase. So, therefore, temperature would also increase. So, heat capacity would be a positive quantity always. So, heat capacity at constant volume is just nothing but the heat involved in bringing a unit increase in temperature of the system under condition of constant volume. With this, if for a system we can evaluate this heat capacity experimentally by looking at measured quantities of heat for unit change in temperature, then we can determine the heat capacity at constant volume. Using this, and this you can see the heat capacity Cv at constant volume, it has two equivalent forms mathematically, dqv by dt and is equal to delta u by delta t at constant v dt. The right hand side of equation 13, extreme right, is just nothing but is giving us the value of partial differential, which we can rearrange. That is, you see, du equals to Cv dt. So, what we can see is now we have rearranged this equation to evaluate the first term in the determination of change in internal energy, this partial differential, by substituting it with just the experimentally determinable quantity called heat capacity at constant volume. We can evaluate this partial differential and can substitute in this equation 10. So, problem for the first part is over with the introduction of a new concept called heat capacity at constant volume. That is, we have correlated change in internal energy with an experimentally measurable quantity in the first term. the partial differential replaced with Cv and multiplied with dt. So, here we have the first term of that equation 10 as equation 14, du equal to Cv dt. Both these change in temperature and change in heat capacities, these can be experimentally evaluated. Now, with using equation 14, we can also determine the finite change in internal energy for a particular finite change in temperature just by integrating equation 14. What we will get as the left hand side, we will get delta U, the finite change in internal energy as the difference of internal energy associated with the final and the initial state, which is equal to integral T1 to T2 Cv dt. Now, it is important to understand that if we want to evaluate this integral and to determine the change in internal energy, we need to establish the dependence of heat capacity at constant volume on temperature. That is, we would like, then it becomes important to understand that how heat capacity at constant volume depends on temperature. If it is independent of temperature, then we can take it out of the integral and then we can easily integrate the integral dt, integrate the differential dt within limits T1 to T2 and we can get delta T as the finite integral value, and therefore, delta U becomes equal to Cv dt. So, in this manner we have evaluated the change in internal energy with change in temperature. So, now it is time to see as if how the change in volume can also be correlated to the internal energy. The first attempt was made by Joule itself. He performed his famous Duel experiment, in which let us have an illustration through this projection of the experimental setup. What he did take a glass bulb which was also connected with another glass bulb through a glass tube, and there was a valve in between. The bulb B was completely evacuated and the bulb A was filled with a working substance, that is gas, and this arrangement was immersed in a water trough, which was there was a thermometer which was also inserted in this water trough, and apart from this there was another entity, here is not shown, that is a paddle wheel. So, that if there occurs any change by virtue of change in state, there occurs any temperature decrease or increase, then the from the system either the heat can be taken up by the surrounding, that immediate surrounding, that is water in the water trough, or water in the water trough can supply thermal energy heat to the system whenever system undergoes a change in state. What he did is he opened the valve and allowed the gas which is being filled in bulb A to expand, allowing it the accessibility to the bulb B. Following, since there was no substance in bulb B, it was only a vacuum. So, therefore, the gas did undergo expansion, and we all know, as we studied earlier also, that there is expansion work against a zero external pressure is known as free expansion of a gas, and there is no work is involved during such expansion. So, therefore, no work effect would be observed. Now, only change occurred was that volume of the system did undergo a change, where the volume of the system almost became double of it. That is, the volume, when the volume of the system changes, he wanted to correlate this change in volume with that of the change in internal energy. Now, he did observe that in the thermometer there was no change. So, he said that since there is no work involved in the expansion process, and moreover since the temperature is also not changed, so it means that there is no heat effect or the work effect is involved for this expansion process. We can understand it from these projections and equations. He said that there was no work effect, dW equals to 0, since there was no temperature change. He said that heat effect is also not involved. If now you just have a look at the first law equation, if there is no heat effect, there is no work effect, and there is change in internal energy which is 0. So, he concluded that the rate of change of internal energy with volume is 0, that is delta U by delta V at constant temperature T equals to 0. In other words, the internal energy of the gas does not depend on the volume of the gas enclosed. This was a mistake in fact. How it was a mistake? It was later shown by the Joule-Thomson experiment itself that the experimental observations which Joule made in his famous Duel experiment, there were certain lacunas associated in the experimentation part itself. What were the lacunas? The main lacuna was actually that Joule had taken a large vat of water. Now, water is known for its very high heat capacity, and moreover the working substance was just the gas, which was also confined in a small volume element, that is a bulb. Now, when it did undergo expansion, it could be involved in heat effect due to furthering separation between the gaseous molecules or atoms, but that heat effects were too low to be observed experimentally, considering the difference in heat capacity of the gaseous species, which produced a magnitude of heat effect which was too low to be determined experimentally due to the experimental limitations that large vat of water was used, which was having very high heat capacity. Because of its high heat capacity, not appreciable, or in other words, even any change in temperature was observed. So, his conclusion, he is reaching to the conclusion that with change in volume at constant temperature, the internal energy of system remains constant, was an experimental mistake and is actually not true. Now, if it is not true, then now the objective is how to determine again this partial differential, so that we can correlate it with that of total change in internal energy, and we can determine the finite change by integration purpose. So, it becomes important to evaluate this integral del U by del V at constant T, that is rate of change of internal energy with volume at constant temperature. To evaluate this, we also need to understand it is this value is very small. The value of this partial differential is very small for gaseous species. However, this partial differential, or in other words rate of change of internal energy with volume value, is very high, although very high for liquids and solids, the condensed phase matter. But the fact of matter is that change in internal energy du as a second term depending upon the volume change is a product of this partial differential del U del V at constant T multiplied with change in volume dV. The fact of matter is that for solids and liquids, because of their high compressibility, very high compressibility, the volume change during a particular change for a very small change in temperature is the volume change for these condensed phase matter is very small value. As a result, because of small volume change for liquid and solid phase, the contribution of volume change towards the internal energy change of solids and liquids is very small, and hence we can even go without, if not precise calculations are needed, we can eliminate the second term in the equation which is used for calculation, the equation 10 which is used for calculation of internal energy, that is du equal to delta u by delta t at constant v dt plus delta u delta v constant t dv. So, therefore, this second term, that is the contribution of volume change towards the change in internal energy, is very small. This whole second term is very small. Then therefore, the second term here in this equation 10 can be eliminated, and we can consider that internal energy is practically a function of temperature only for gaseous as well as for solids and liquids. The reasons are different. For the gaseous phase, for the gaseous system, the rate of change in internal energy with volume is at constant temperature is very small and very insignificant to be determined practically. However, for solids and liquids, this partial differential is although very high, having a very high magnitude, but the total change in volume is very small. As a result, for very small change in condensed phase matter, again this second term contribution is insignificant for change in internal energy, and we can proceed for calculation of change in internal energy for all practical purposes, taking it as only the first term and evaluating it by taking its integral. So, this is how the first law of thermodynamics is being used to determine change in internal energy of the system, and conceptualizes basically makes a concept of internal energy and helps in determining it, changes in it. Thank you very much.
Thank you, sir. Thank you so very much for giving a broad outlook on first law of thermodynamics. I hope that in future sessions also we would be discussing more. New topics under this series, chemical thermodynamics. Till then, friends, if you have any queries, or if you want to give your feedback regarding this particular lecture, or if you want to have a lecture on particular topic, definitely you can mail us at info.cec@nic.in. Till then, you can watch our lectures with the help of the YouTube, which we daily upload for you, so that it becomes easier for you to study your course material. Thank you, sir. Thank you once again.
Thank you very much.